In this video, we're going to take a look at membrane permeability of small molecules, which includes drug molecules. With our membrane permeability, there is going to be a balance between both water and lipid solubility. We're going to need adequate water solubility in order to have dissolution of our product, if this is a drug, and then adequate lipid solubility for penetration across the membrane. So if we look at this curve, we see our drug activity on the y-axis, lipid solubility on the x-axis. So you see we get a lower activity at the two extremes, where somewhere in there is a maximal effect when you hit that balance between the water solubility and lipid solubility correctly. What we'll see is that the polarity of the molecule will determine our absorption rate, where the charged or highly polar molecules pass through the membrane rather slowly, and those neutral hydrophobic molecules pass more readily. So if we look at factors affecting permeability, so here we're looking at our flux or rate of transport across the membrane. This is our concentration gradient. We know that as we increase our concentration, we're going to get an increase in the rate of that, once you lose the concentration as you head towards an equilibrium, right, that becomes very small, your net flux. And so we see a higher, regardless of the nature here, our low permeability molecule, we get an increasing rate or flux across the membrane with increasing concentrations. The same is true for the high permeability molecule. We just have a difference in the slope, where we have a much steeper slope for the compound with a high permeability. So if we look at the factors that affect membrane permeability, we see that those are listed here. So the lipid solubility of the diffusing substance, the more lipid soluble, the greater or higher the permeability of that is. The size and shape of the substance, so the larger and more irregular in shape the molecule becomes, the lower its permeability will be. Then there's some other factors not related to the structure of the molecule that are important. So temperature. At higher temperatures, you're going to see greater permeability. We rarely see this become important because the body temperature is pretty consistent and well regulated. And the last factor that affects membrane permeability will be the membrane thickness. So the thinner the membrane, the more easily things will be permeable to it. Thicker, it's more impermeable to substance. Of all of those factors listed, I have down here the lipid solubility will have the strongest influence on permeability, since most substances in the body will be hydrophilic and won't easily cross the lipid bilayer. So if we look at that lipid bilayer, remember our individual units are cylindrical. So you have the polar head group represented by the blue sphere, and then we have those side chains that are relatively nonpolar or lipophilic heading down. So we are going to have the polar head groups on either side of the bilayer, and then in the center is all those lipophilic tail groups or nonpolar tail groups. And since there's a greater distance or a larger portion is the nonpolar region of the bilayer, it's going to be impermeable to polar or charged compounds. It'll be very difficult for them to get through, or you can think of it as the rate net flux will be very, very small. And we'll see that the permeability of small molecules is going to be correlated with their relative solubility, both in water and nonpolar solvents. When we talk about the way that the small molecules cross the membrane, what they're going to do, just as a reminder, everything is usually well solvated or dissolved in water. So in this example, we'll look at a sodium that's solvated. So there are 6 water molecules tightly associated with that. So for this sodium to cross the membrane, it's got to shed those water molecules. So it's not going to go across as the hydrate. It's going to go across as just an individual sodium. So it's going to shed the water, then it'll get into the membrane, and once it gets through to the other side, it will be resolvated by the water. So those would once again surround the sodium. And what we see is that ions have a lot of trouble because the replacement of the shell of polar water molecules with those nonpolar interactions within that core of the membrane is very unfavorable energetically. And we'll look at that more closely in class. So if we do take a look at our permeability, two different small molecules, this is our looking at permeability and how likely it is to cross there. So this is in a centimeter per second is our permeability. So things at the right end where we have high values would have high permeability. And then things at the lower end, the polar charged ions, have low permeability. And most things then fall in the center. So if we do some comparisons, we see that sodium and potassium are going to traverse through the membrane 10 to the 9 times, so a billion times more slowly than water, so it's very, very slow. And then just to get a feel for this, tryptophan, one of the amino acids we've talked about, we know that that's Zwitter ionic at pH 7, right? So it has a net charge of 0, so it's a net neutral molecule because the minus 1 charge and plus 1 charge cancel each other out. However, that still does affect the polarity or ability of this molecule to cross the membrane. If we take a look at indole on the right-hand side here, that's basically the side chain of tryptophan is an indole group, and then that's just bound to our generic alpha amino acid having the alpha carbon with the NH3 group, CO2 minus group, and then a hydrogen atom. So if we compare their ability to cross the membrane, the indole is 10 to the 3, so times more able to cross the membrane. Sorry, 10 to the 3. Because it's lacking those polar charge groups. So if we take a look at, this was in your slide set, and we wanted to rank these in terms of our permeability, our indole, very nonpolar, would have the highest ranking, so that would be the most permeable to the membrane. That'd be followed by our glycerol, not charged, but it is starting to incorporate some hydroxyl groups. Then our glucose, same thing, we now have more hydroxyl groups compared to the glycerol, so that's going to have a little harder time. That's followed by our tryptophan amino acid. Again, remember these groups are going to be ionized at physiological pH, and then our lowest solubility would be the charged ion. All right, so hopefully that was helpful, and that wraps this video up.